Okay, so this is the answers for the practice questions labeled 316 for video instruction. I wanted to take the opportunity to be able to go over some of the answers and give you some ideas of how to effectively answer the questions that are being asked so you can optimize the number of points that you receive. And with that, I'll go over through the answers. This assignment should be done after you've done the intermolecular force assignment, just so that you're ready for understanding those principles and answering some of the questions we have here. I also did include some other questions that are in there so that you can keep practicing, because we're getting closer and closer to the AP exam day. All right, so with that, let's get started. So question number 1 says, using the principles of atomic structure and or chemical bonding to explain each of the following. And you must reference both substances. So when we're talking about referencing both substances, it's not a bad idea to actually just include a T-chart. So we're talking about the radius of lithium is greater than the radius of beryllium. So this one has a greater radius. So this one would have a smaller radius. So since it's going to be based on atomic structure or bonding, this one has to be atomic structure because we're talking about atoms. So if we look at the atomic structure for lithium, its configuration is 1s2, 2s1, and for beryllium, it's 1s2, 2s2. And then we know that, so that's going to help you kind of look at the size. And then we know that lithium has 3 protons, while beryllium has 4 protons. So if we're talking about which one is larger and smaller, then it should make sense that we're going to be talking about the effective nuclear charge. So we're going to just start off with the effective nuclear charge. For beryllium is greater than that of lithium. Beryllium has 4 protons attracting the 2s electrons, while lithium has 3 protons attracting the 2s electrons. The stronger attraction from beryllium's 1 extra proton decreases the radius due to its additional attractive force. Okay, so we're looking at that it's going to attract those valence electrons with a stronger force of attraction due to the fact that its effective nuclear charge is greater, due to the fact that it has an extra proton in the nucleus. Okay, so that's what you needed to talk about. That particular question was 2 points actually, based on the rubric. So it was 1 point for indicating that beryllium has more protons than lithium, and 1 point for indicating that since the electrons are about the same distance, there is more attraction in beryllium as a result of the larger number of protons. Both lithium and beryllium have their outer electrons in the same shell. However, beryllium has 4 protons and lithium has only 3. Therefore, the effective nuclear charge experienced, or the attraction experienced by the valence or outer electrons, is greater in beryllium than it is in lithium. So beryllium has a smaller atomic radius. Okay, so that's what the scoring guide says. and identified. So for mine, I identified the two s electrons, which were the valence electrons. So that would be worth 2 points as we're looking at it. All right, the second one is the second ionization energy of potassium is greater than the second ionization energy of calcium. So we're going to be comparing the second ionization energy of potassium is greater than the second ionization energy of calcium. So keeping in mind that for potassium, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And for calcium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So when we're talking about its second ionization energy, the second ionization energy for potassium is a potassium ion plus energy, which is your ionization energy, is going to give you a K2 plus. And the second ionization energy for calcium is going to be calcium plus energy to give us calcium 2 plus. So this is the ionization energy that we're talking about, that this ionization energy is greater than this one. Well, if we go back and we look at its configuration, we're going to be taking it from a 1 plus ion. So if we take it from a 1 plus ion, that electron isn't going to be there. So that means that we're going to take it from the core electrons, where if we take away, if we look at a calcium 1 plus, this is going to be a 4s1. That's the configuration, so that's the energy that we have to put in to take out that 4s1 electron. So this is going to be taking an electron away from something that's in the fourth energy level, where for potassium, we're taking an electron away from something that is a core electron. So that means that it's going to require more energy to remove that electron from the calcium 1 plus ion than it is to remove it from the potassium. It's going to take less energy to remove it from the calcium 1 plus ion compared to the potassium 1 plus ion. Okay, and the key said for this one that it was also a 2-point question. 1 point is earned for saying that the electrons are removed from an inner level in potassium, but 1 level higher, the fourth energy level in calcium. And 1 point is earned for saying that the distance to the nucleus is less for the third level, so attraction is greater, more energy is needed to remove an electron. The second electron removed from potassium atom comes from the third energy level, the inner core, and the second electron removed from a calcium comes from the fourth energy level, which is the valence level. The electrons in the third level are closer to the nucleus, so the attraction is much greater than for electrons in the fourth energy level. Okay, so those were the 2 points that they were looking for in that question. The biggest thing is to remember that they're describing the second energy level, the second ionization energy, and not the first ionization energy. Okay, so that was question B. So now we go on to question C. The carbon-to-carbon bond energy in C2H4 is greater than the bond energy in C2H6. So we have C2H4 is greater than C2H6, and in this case we're talking the bond energy. So that means that we know that the bond energy is different. We know that the bond energy for multiple bonds is greater than that for single bonds. So that means that this is going to likely require us to make a Lewis structure. So for C2H4, C2, we go to H4, 1, 2, 3, 4. So there must be a double bond. And C2H6, there's going to be 3, and C2H6, there. So the carbon to carbon bond energy, so they're talking about these bonds here. So the carbon-carbon bond energy in C2H4 is greater than the carbon to carbon bond energy in C2H6, because in C2H4 the carbons are double bonded, whereas in the C2H6 the carbons are single bonded, and a double bond has a greater bond energy than in a single bond. So as far as the key goes, it says 1 point is earned for indicating that C2H4 has a double bond and C2H6 has a single bond. 1 point is earned for indicating that the carbon-carbon double bond requires more energy to break it, is stronger than the carbon-carbon bond in C2H6. So as long as you said each of those, that would be worth 2 points in this explanation. Okay, and then the last one is the boiling point in Cl2, we're talking boiling point, is lower than the boiling point in Br2. So if we're going to compare boiling points, that means that we're talking about the strength of force. So that means the attractive force for Cl2 is less than the attractive force in Br2, right? And that comes directly from the fact that they're telling us that the boiling point is less than or lower than that of the boiling point of bromine. Now, when we're looking at boiling, we know that for both of them, we're going from a liquid to a gas. So we're looking at a phase change. A phase change requires and when we're talking boiling, the breaking of the intermolecular force. So we do have to identify the intermolecular force. So we know that this force is going to be less for chlorine than it is for bromine. Well, chlorine is diatomic, so that would be its Lewis structure. And bromine is diatomic, so that would be its Lewis structure, which means they are both nonpolar. And since they are both nonpolar, the intermolecular force that we have to be describing is London dispersion forces. So bromine has to have a larger London dispersion force because it has a more polarizable cloud due to a greater number of electrons in the bromine molecule compared to the number of electrons in the chlorine molecule. And the increased polarizability of the cloud is going to produce a greater attractive force, which is going to create a stronger or a higher boiling point. Okay, so from the rubric, it says 1 point is earned for indicating that chlorine and bromine are both nonpolar and or have only London dispersion forces. And 1 point is for indicating that more electrons, the more polarizable, the greater the dispersion forces, and the higher the boiling point. So notice all those pieces have to be there. So that's why it works very well to break it down. If you just said that bromine has a stronger London dispersion force than chlorine, you actually would not, you have only gotten 1 out of 2 points in this case when I look at the rubric. Okay, so make sure that that you're clear and that when you're answering the questions, you include support for the phenomena that they're describing. So here it has to go back to the boiling point. It has to describe that a higher boiling point means that more energy is required because there's a greater attractive force between the particles. Okay, so that's question. And now question number 2. So answer each of the following in terms of the principles of molecular behavior and chemical concepts. So we have the structures for glucose, C6H12O6, and cyclohexane, C6H12, are shown below. So this one is going to be the C6H12O6, that's the glucose, and this is the C6H12. And I can tell by looking at them because one, the glucose was mentioned first, and so that's the one that you see first, and two, it's the one that contains the oxygen. So it says identify the types of intermolecular forces in pure glucose and pure cyclohexane. So this means that they just want to identify means you're going to list. So if I have the two of them, I'll just erase that for a second. I have glucose and I have cyclohexane. So when I look at the two of them, glucose is going to be polar. If it's polar, then it has to have dipole-dipole. And I have to see if it's polar, it has dipole-dipole. Does it have hydrogen bonding? Does it have HNOF? Well, I look at OHs around here, so that means that it has hydrogen bonding. But I also have to remember that it also has to include the fact that any molecule is going to contain or have London dispersion forces as well. So this one's going to have the London dispersion forces. So cyclohexane, if I notice that it has symmetry, I know that it's nonpolar. So since it's nonpolar, the only force of attraction that it can have is London dispersion forces. Now, the question asks just to identify. I wrote down polar and nonpolar just to help me process the question that's there. What they were looking for, and I could go through and, it's okay that I include both dipole-dipole and hydrogen bonding. What they're going to care is that I have the hydrogen bonding and the LDF, and then for the cyclohexane that I have the LDF. So the response says 1 point is earned for the correct answer. Hydrogen bonding or dipole-dipole interactions or London dispersion forces may also be mentioned. 1 point is earned for London dispersion forces for the cyclohexane. Okay. And then for part B, it says glucose is soluble in water, but cyclohexane is not soluble in water. So what we have to remember, and we have to be careful when I say this because it's not an explanation, but it does help us to remember that, and I see this a lot when I score the AP, is that we don't want to use this as an explanation, but it helps to remember that likes dissolve likes. So what that means is polar substances dissolve polar substances, nonpolar substances dissolve nonpolar substances. So when we look at glucose, we know glucose has hydrogen bonding. Water has hydrogen bonding. And cyclohexane has just London dispersion forces. Now this also has London dispersion forces. This also has London dispersion forces. So, but what like dissolves like means is that the glucose and water have the ability to interact because they have the same types of intermolecular forces. Now, it does help that when we're looking at polarity, that dipole-dipole will interact with something that has hydrogen bonding. But the best solubility happens when we're dealing with so hydrogen bonded substances will dissolve very well in water because it can also hydrogen bond with the water. So in this question, you should have mentioned that glucose is soluble in water because it has similar intermolecular forces that can interact with the water. The hydrogen bonding of the glucose can hydrogen bond with the water, which allows it to dissolve in water. Cyclohexane is a nonpolar molecule and only has London dispersion forces as an intermolecular force. Therefore, it cannot interact with the water in the same way, and that's what makes it not soluble. Okay. So it says 1 point is earned for explaining the solubility of glucose in terms of hydrogen bonding or dipole interactions with water. And 1 point is earned for explaining the difference in the polarity of cyclohexane in water. So it says the hydroxyl groups in glucose molecules can form strong hydrogen bonds with the solvent water molecules. So glucose is soluble in water. In contrast, cyclohexane is not capable of forming strong intermolecular attractions with water, no hydrogen bonding. So the water cyclohexane interactions are not as energetically favorable as the interactions that already exist among polar water molecules. So that's what it's looking for question B. Okay, so the next question was part C. So notice that we're given two equations, and it's going to help very much if you just kind of identify those equations. So we have process 1, and just kind of, I'm going to rewrite it just to kind of underline it. So this is process 1. So we have water as a liquid going to water as a gas. So we can identify this right away. This is a phase change, right? Because we're just changing liquid to gas. And it says delta H naught is positive 44.0 kilojoules per mole. So what this identifies is when we see a positive delta H, that means that this is an endothermic process. This tells us how much heat is required for this phase change to occur. The second one that we have is the H2O liquid goes to H2 gas plus 1/2 O2 gas. And it says that the delta H naught here is positive 286 kilojoules per mole. So this is not a phase change. This is an actual reaction, right? Because when I look at it, the water is a liquid. There is no water on the right-hand side, where in the first equation, there's water on both sides. So the question I says, for each of the two processes, identify the type of intermolecular or intramolecular attractive forces that must be overcome for the process to occur. So in step 1, we're looking at that it's a phase change. So if we're talking about vaporization, so the vaporization of water requires intermolecular forces to be broken. And those would be the hydrogen bonding force of attraction. Right? That's what we see in number 1. Then when we look at number 2, how does that differ? So now this is where when I tell you that, we have to be careful about how we word things, you'll see it here. So in this case, we are looking at water's intramolecular bonds must be broken to form H2 and O2. The bond that are broken are the oxygen-hydrogen bonds within the water molecule. Right? That's what we see. So when I look at question little I, it says 1 point is earned for identifying the type of intermolecular force in process 1. So in process 1, hydrogen bonds in liquid water are overcome to produce distinct water molecules in the vapor phase. In number 2, 1 point is earned for identifying the type of intramolecular. So here we're looking at the covalent bonds that exist between the oxygen and the hydrogen. So, which I didn't say covalent, I should have said covalent. But I actually still would have gotten the point for it just because I labeled it as OH here, which would be assumed to be covalent bonds. Okay, and then the next question says, indicate whether you agree or disagree with the statement in the box below. Support your answer with a brief explanation. So it says, when water boils, water molecules break apart to form hydrogen molecules and oxygen molecules. Well, what they're saying then is that process 2 would be what happens when we're boiling water. So we would want to say something about boiling water is a phase change and only intermolecular forces are broken between the water molecules. Once the hydrogen bonds are broken between the liquid molecules, steam will be formed. It is not the covalent bonds that are broken. And then the really important piece, therefore, I disagree with the student. And just to be clear, as a score, if it does not say disagree, I stop right there. So I have to see that there was a disagreement. No disagreement means 0 points, even if I wrote everything that was there. If you write what's there and you're incorrect, then you're incorrect. So that would be 0 out of 2 points. But in this case, you have to say I disagree. And then once you say I disagree, you have to have the correct description. So in this case, it was based on the fact that you're breaking intermolecular forces and not intramolecular forces. So that would be the 2 points that you could earn there. Okay, so now we move on to we're still in the same question. Now we're on the next section of the same question. So now we're given identify 2 diagrams that could represent a catalyzed and an uncatalyzed reaction pathway for the same reaction. Indicate which 2 diagrams represent the catalyzed reaction pathway for the reaction. Okay, so I'm just going to draw on the bottom here just to help you interpret this. This is not something that we've learned yet. This is something that we're going to learn within this next unit. So this is a potential energy diagram. So I want you to notice that all of them start in the same section. Then we have this hump. And then what happens after the hump depends upon what the substance is. But the hump, if I just over exaggerate in this case, what we look at is this is the reaction progress. So that means right here we have our reactants, and here we have our product. What this hump actually represents is what's known as the activation energy. And activation energy is something you likely heard about in biology because a catalyst lowers the activation energy, and the catalyst that you would have been describing would be enzymes. So if I lower the activation energy, so the activation energy always comes from where the potential energy is of my reactant, and it goes up to the top of this complex here. This would be known as the energy of activation. So if I added a catalyst to it, it wouldn't change the difference in energy between my reactants and products. We actually call that delta H. Instead, what we would look at doing is the catalyst would lower the activation energy. And by lowering the activation energy, a catalyst is going to make a reaction go faster. And that's really helpful, especially when you have some reactions that could be very, very slow. So in this case, we want to have two diagrams that can represent a catalyzed and an uncatalyzed reaction. So that means that if it's the same reaction, delta H has to be the same. So that means then that the distance between here and here has to be the same for those reactants. So if I look at that, the only two that are the same are diagrams 1 and 2. So these two aren't possible. So identify the two diagrams that could represent a catalyzed and an uncatalyzed reaction pathway for the same reaction. Well, that's going to be then diagram 1 and diagram 2. And it just says to identify, and then indicate which one represents the catalyzed and the uncatalyzed. So now what we would want to do is compare what I like to call the hump of the camel. So the activation energy. This activation energy is greater than this one. So diagram 1 would be the catalyzed reaction, and diagram 2 would be the uncatalyzed reaction. Okay? And then agree or disagree. Indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. Adding a catalyst to a reaction mixture adds energy that causes the reaction to proceed more quickly. So a catalyst does make a reaction proceed more quickly, but it doesn't add more energy. It actually lowers the activation energy. So in this case, I would just say that I disagree with the statement, a catalyst does not add energy, rather it provides what's known as an additional pathway for the reaction to proceed that's going to lower its activation energy. So again, this is something we'll be learning about next week, but it's part of the question, so I wanted to give you a chance to be able to answer it. Okay, so now let's go on to question number 3. So it says, answer the following questions relating to HCl, CH3Cl, and CH3Br. A. HCl can be prepared by the reaction of concentrated H2SO4 with NaCl as represented by the following equation. So we have H2SO4 plus 2 NaCl, which is solid, to give 2 HCl gas plus Na2SO4 aqueous. And it says a student claims that the reaction is a redox reaction. Is the student correct? Justify your answer. So we know that if it's redox, that means that we have to have changing oxidation numbers. So we have to look and see, do any of the oxidation numbers change? So we know that oxygen's going to be -2, hydrogen's going to be +1, sulfur then is going to be +6. Sodium is going to be +1, chloride is going to be -1, hydrogen is going to be +1, chloride is going to be -1, sodium is going to be +1, sulfur, oxygen is -2, and sulfur is +6. So I would have to say the student is incorrect. The reaction is not a redox reaction because the oxidation numbers do not change state. Therefore, it's not a redox reaction. And for that question, it was 1 point. And for stating that it's not, no, the student is not correct and that none of the oxidation numbers changed. And, if you just write this, so even if you went in and you wrote that up here, and then stated that the oxidation numbers did not change, that's just fine. Because in your answers, you would have had a space between there. Or what you could have done is done what I did and rewrote the equation and then just included the oxidation numbers. Okay, question 2. Calculate the mass in grams of sodium chloride needed to react with an excess of sulfuric acid to produce 3 grams of HCl. Assume that the reaction goes to completion. So this is a straightforward reaction. So now I'm going to look at, I have excess, so I know that I have more than enough, and I want to figure out how many, what mass in grams I produce of this. So I have 3 grams of HCl, and then I want to get that into moles, so I know that in 1 mole of HCl, there's 36.46 grams of HCl. So that's going to give me the number of moles. So 3 divided by 36.46 is going to give me 0.08228 moles of HCl. And then I know for every 2 moles of HCl, I have 2 moles of NaCl. So that means that I'm going to have 0.08228 moles of NaCl, and they wanted grams. So that's going to be 22.99 plus 35.45 is 58.44 grams per 1 mole. I'm going to end this with 2 sig figs. So that gives me 4.8 grams of sodium chloride that's produced. And the answer, I must have, when I copied this, it must have dropped off a 0. So it was looking for 3 sig figs in the answer. So it was 4.81, which I got my question here only had 2. So based on that. So, yep, that would be the answer for that one. And that work was actually 2 points. 1 point for determining the number of moles of HCl, and 1 point for calculating the actual mass of the sodium chloride. So again, that also helps that if this answer was incorrect, you would get 0 points for it. But then as long as this answer agreed with it, then you could get full credit. Okay, question B, it says we have ethanol plus hydrochloric acid yields methyl chloride plus water gas, and you're given this Kp value, which you don't know anything about. So it says CH3OH and HCl are combined in a 10-liter sealed vessel and allowed to reach equilibrium at 400 Kelvin. The initial pressure of this methanol in the vessel is 0.250 atmosphere, and that of HCl is 0.6 atmosphere. So I don't know anything about what Kp is. And I'm just going to try to see if I can figure something out. So I have CH3OH gas plus HCl gas to give me CH3Cl gas plus H2O gas. So I noticed that like all of these are gases, okay, and I have volume is a 10-liter container, and I know that the temperature is 400 Kelvin, and then I've got this weird Kp value, which is 4.7 times 10 to the third value, which is a big number, okay. And then I'm told the initial partial pressure of the methanol in the vessel is, so that's to start, is 0.250 atmosphere. And that of HCl is 0.600 atmosphere. And it says, does the total pressure in the vessel increase, decrease, or remain the same as equilibrium is approached? Justify your answer in terms of reaction stoichiometry. So when I look at this answer, I know that I'm starting with 0. I don't know anything. I don't know if you could actually make something up for this one or not. But I think you could choose whether it increases, decreases, or remain the same. And then just make something up if you could, right? I guess it's kind of worth that. Question number 2 says, considering the value of Kp, calculate the partial pressure. Okay, that one you're not going to be able to do. And then question number 3, at this point, you're not going to be able to do either. So I guess for this question, we're going to call it even and say, all right, I'm not going to worry about the points here. But let me just make a point here for you. The other questions that you have, this is all part of the same question. I didn't change anything about the questions. So for B, little I, that was worth 1 point. B double I was also worth 1 point. And B triple I was also worth 1 point. So this whole question was worth 1 point each for a total of 3 points. Whereas the previous questions were all worth 2 points each, and you could answer all of them. So even if you came across something like this and you kind of worked it out, sometimes you might even have something in here that's hidden that you might be able to take a good guess at. You should have the ability to be able to still do well, even if you come across questions that you don't know. Okay, and I want to tell you that and help you to understand that, because I'm not sure, if I'm pretty positive that we're not going to be able to finish everything, but I don't want you to be discouraged. I want you to remember that this game is all about trying to get as many points as you can. All of the other questions that we had were 2 point questions. This one means that I just don't earn 3. Well, if you get a 78% on the AP test, you can still get a 5. So that gives you 22% to work with. And these 3 points are minuscule compared to the other points that are available. So I just wanted to kind of throw that at you, just to kind of help you to kind of see that you really shouldn't get discouraged. Just go in with the mindset that we're just going to do what we can do. And hopefully you'll know more answers than you don't know, right? Or you'll be able to figure something out more than you can't. So that was the point I wanted to make with this question. But this question you can answer. So letter C, we have methyl chloride and methyl bromide. We're told we have the compound, the molar mass, the dipole moment, the boiling point, and the heat of vaporization, which the heat of vaporization is the amount of heat that's required to vaporize. So whether we're looking at evaporation or if we're looking at boiling, it's the amount of heat we have to go in to be able to do that. Okay, letter I. Identify all the types of intermolecular forces that exist among molecules in methyl chloride. So one of the things that you want to look at is that it says to identify all of the types. So we have CH3Cl. So CH3Cl. So right away, I can see that this has to be a polar molecule. So in answering question number I, it's going to be London dispersion forces because it's a molecule, and dipole-dipole. It doesn't have hydrogen bonding because it doesn't have hydrogen bonded to nitrogen, oxygen, or chlorine. Okay? So now little double I. In terms of intermolecular forces, explain why the boiling point of methyl bromide is greater than that of methyl chloride. So we just identified the intermolecular forces that exist in the methyl chloride. So if we compare that to the methyl bromide, we have CH3Br. And once again, this is going to be a polar molecule. But we know that the electronegativity of chlorine is greater than that of the electronegativity of bromine based on its placement in the periodic table. Now, I can also tell because they give me this section right here on the dipole moment. And remembering that the dipole moment identifies the strength of the polarity. So for the methyl bromide, it's 1.81 debis. And for the methyl chloride, it's 1.87 debis. This is a greater number than that. But what it says is this one here actually has the higher boiling point. So that means that it has to have the stronger IMF, right, intermolecular force. If it has the higher boiling point, it has to have the higher or stronger intermolecular force. So I know that it can't be due to the fact that they're both polar because this one has the stronger dipole moment. It's more polar than the methyl bromide. So the only thing that can also be different is the London dispersion forces, right? They both have to have London dispersion forces. And if I look at the periodic table, bromine is a larger atom than chlorine is. So that means, therefore, its London dispersion forces must be greater than that of the methyl chloride because bromine's electron cloud is more polarizable than that of the chlorine's cloud. So that's going to make it have a stronger intermolecular force, which means it's going to require more heat energy in order to be able to break the intermolecular force between the molecules. And again, that makes sense because the heat of vaporization is shown to be greater for the methyl bromide than it is for the methyl chloride. Okay? And then we have one more question. It says a 2 milliliter sealed glass vial contained 1 gram of methyl chloride is stored in a freezer at 233 Kelvin. Calculate the pressure in the vial at 298, assuming that all of the methyl chloride vaporizes. Okay, so let's look at what that looks like. Okay, so we have a 2 milliliter sealed container that has 1 gram of methyl chloride, and it starts at 233 degrees Kelvin, but we're going to make it go up to 298 Kelvin. So it wants to know what is the pressure. So in this case, we're going to rely on PivNert, right, to calculate the pressure. And so the volume here is in 2 milliliters. When I use my volume, I have to put that into liters. So that's going to be 0.00200 liters. And then I have 1 gram of the methyl chloride. So I have to take the 1 gram and I have to convert that into moles. So that's going to be 12.01 plus 3.03 plus 35.45 gives me 50.49 grams. So I'm going to take 1 divided by that number. And that means that I have here 0.01981 moles. And then I have the temperature in Kelvin. So I'm going to go ahead and I'm going to solve for P as nRT over V. And I'm going to look at N is 0.01981, 0.08206, 298 divided by 0.00200 liters. So the pressure is 242 atmospheres. So that should be my answer to little I. And then it says, explain why it would be unsafe to remove the vial from the freezer and leave it on the lab bench at 298 Kelvin. Well, 233 it's in a liquid state. With all of that is going to vaporize at room temperature. 242 atmosphere is a whole lot of pressure for a 2 milliliter vial. So that means that its internal pressure is going to be much greater than air pressure, which means it's going to explode. And explosion would be bad. So that would be why it would be unsafe to leave it out. Okay, so those are the practice questions that I wanted to show you. I hope that it was helpful in helping you think about the thought process. And from this point, you guys can go right ahead on and answer the questions that are in my AP Classroom. Okay, so good luck.